All right. It's a great, great pleasure to be here today and to give a talk in this conference in honor of Peter. I know Peter for a long time, I think over 30 years now. Yes, Peter, we are not that kids anymore. Right. And met him first time. Well, I heard of him still before I came to the United States, but met him first time in Texas, cockroach country. And I can't forget one thing. I was giving a series of talks. Peter was really, at that time, relatively younger than me. Not anymore, I guess, right? And yes, he was taking notes from my classes. I doubt he would take it today. Okay, right. Anyway, and since then we got interested in many things and worked together. Published a lot of joint papers. We shared some students. I guess we never disagreed, by the way, right? And there's one main subject of our interest is to prove that some beast does not exist. This is this exceptional character of Landau-Ziegler zero. And we produced a few papers trying to eliminate this guy without success. And in the meantime, there are other, I would say, completely opposite feelings, which I am going to convey today, that we'd be actually very happy if that beast do exist, actually. And the subject is very broad, and I'm sure everybody knows a lot of stuff about this special character. And in particular, very impressive is the impact of the existence of this special character on the distribution of prime numbers. We have lots of papers jointly with John Friedlander. But today I would like to focus on the impact of these illusory characters of discriminants on the distribution of zeros, particular zeros of L functions on the critical line. I mean, it's amazing how far is the impact of that character reaches. Go to very remote places that at first glance you don't see any relationship whatsoever. And even though we don't believe that such character will exist, it would violate the Riemann hypothesis. But maybe even the Riemann hypothesis has an exception. Some people believe it. So I think it's still there's a point to speculate about how this character impacts on various areas, mainly for educational purpose, to see where we are and what is really. Oh, I can't see the screen really. Yeah. Well, I have my notes. I see everything here. Right. Okay. Now, yeah. I'm reading from my notes. All right, thank you. Actually, it wouldn't be bad if you didn't see anything. Okay, yeah. Right. So I'm talking about the impact on zeros of L functions, and this is an everlasting joint project with Brian Conrey from AIM Institute. It's still a work in progress, even though I think we are almost finished. The references are not written down, but so let's go. Yeah. So let me make warm up a little bit and say what we know about the zeros, critical zeros of L functions. And even though we be specialized for L functions related to quadratic number fields, let's start generally a bit so it would expose the ideas probably better. So we consider L function, which is civilized, a Euler product. It could be arbitrary degree, but let's, for notational simplicity, take degree 2 Euler product. It has Maybe I should I use pointed, or you can read my mind? I think, yeah. I don't know how it works. It just doesn't send any feedback from it. Anyway, and let's assume Ramanujan conjecture. Why not? Just for the exposition. And it satisfies functional equation, lambda of S, which is a product of L function times local factors at infinity, and conductor Q, or sort of the number, right? And so G is here a product of gamma factors. In this case, for GL2L functions, it's a product of 2 gamma factors. It doesn't matter really for what we'll be doing later, but just for notational simplicity, let's focus on these. So we have this almost self-dual functional equation. Lambda is equal to eta times lambda bar 1 minus S bar. Eta is the root number, and kappa 1, kappa 2 are these parameters, shifts in the gamma factors, and Q is essentially a conductor. An abstract number so far, okay, rather than 1. Right, and so as I said, we'll be interested in the distribution of zeros. So rho denotes usually the zero of a function. It's beta plus a gamma, beta in the critical, beta from 0, 1, so 0 is in the critical strip. And gamma is the imaginary part, the height of the zero. Suppose, let's say, less than t. There are infinitely many zeros, as we know, so we have to count them with certain rectangles. And we count them with multiplicity. So that's not a big deal after Riemann to get asymptotic formula for the number of such zeros in the critical strip. It's 2t over pi log qt plus O of t. You have actually more precise formula if you want. It doesn't matter for us. Let's say t a bit larger than the logarithm of the conductor. And all right. And one point I would like to make here is following Riemann. You see, the main contribution to the counting zeros come from gamma factors, from variation of the argument of gamma factors, which is really surprising how important impact is from gamma factor, much less of the Dirichlet series for a function itself. So it is a warning. It says you cannot omit even a single place in the L function in order to be to reveal the truth. So the variation of argument by Stirling formula gives you this main term in the counting of zeros. It will be technically important to remember that, because how we proceed later, how the main things come from. Right. All right, and then let n sub 0 of t be the number of critical zeros on the critical line, and well, it's equal to the total number of zeros. Now, let me tell you a secret, Peter. It has never been proved yet. Yeah, right. We have appetite for that, but maybe next, 71st birthday of you, right? Okay, no promise, but I will try to work hard. Okay. Right now. Right. Okay. So. What is known, let me be brief. Let's say for zeta function of Riemann, even though it's GL1, I think. If you count the numbers of zeros in a narrow rectangles, then it is a relatively small number. It's estimated first by Carlson, 1921. It's called density, estimates of density theorems. What it reveals that almost all zeros are very close to the critical line, not on the line, but very close to the critical line. And that's standard classical result. So a lot of things is known, I mean, supporting sort of, at least, psychological, the Riemann hypothesis. But the point is what about zeros on the line? It's a very different strategy to prove things there because, estimations, just back estimations of whatever, zeros in a region, by contour integration fails. You have to really touch the zeros exactly on the line, zero-dimensional set. And so there are essentially two different approaches today to count zeros, the critical zeros. Maybe I should start first. Hardy proved that there are infinitely many zeros of the Riemann zeta function. Hardy-Littwood proved in 1921 there is more than t of them. Remember, the asymptotic is t log t of the times constant, so it wasn't really a positive proportion, but quite a number of these were already established that are on the line. And a great breakthrough came in 1942 by Selberg. I think that was really a revelation at the time. He proved that actually positive density of zeros are on the critical line. Let's say kappa is the lower bound for this density. And the kappa was positive constant. He never determined that. It was very, very small. And Peter knows his favorite joke, but maybe at the banquet Peter will tell about this kappa business. And there was a pursuit for very good constants. And the Selberg method was, I mean, there were some constants determined by Selberg method, but extremely small ones. And really substantial progress was made in 1974 by Levinson, not only because he got a very good constant, more than 1/3 of zeros were on the line, but also because he really introduced a new method. Pretty different method. I will address this issue in a moment. And I would say rather complicated even by today's standards. And so he got more than 1/3 of zeros on the critical line. Then I wouldn't say there was a revolutionary, progress beyond Levinson, but there were really technically a lot of great innovations introduced later, particularly by Conrey. That I mentioned that maybe later in a proper moment. And the constant was now more than 2/5 of zeros are on the critical line. Just to make you impression, it uses a lot of machinery from trigonometry, including implicitly or indirectly spectral theory of automorphic forms, right? So just to improve the constant, right? And the best, well, not really best right now, but the best I have seen, and let's say differently, the best I have read was by Feng, who further improved the constant. Not much, but with some innovations about modifier. I'm not sure if I have time to talk much about that. But anyway, you got impression what is known and where is the challenge. No, right. So as I said, there are essentially two different approaches to count zeros on the critical line. And even though I'll be really talking about Levinson's method, I think by comparison it's really important to maybe spend a few minutes and talk about Selberg method, because then you see some kind of a difference in thinking, or also in better perspective. So already starting from Hardy and Littwood, you take a zeta function on the critical line, multiply by by this g factor, which is coming from these gammas in the functional equation, and normalize it so that function f of t defined this way is real on the critical line for real t. And so in order to study how many zeros are there, you just enough to study the sign changes as t runs over a segment or real segment. That was the idea, and the way it is done is just simply. Remember, we have very hard time difficulty to control even the size of the Riemann zeta function on the critical line, and even less the sign change. So it's never really for studying locally. It's really on average studying integrals of various mean value, various kind of integrals over short intervals, and comparing them, and you find out how often the sign change occurs. Well, if you do that, it's not a great job. That's really hard in Litwood, actually. But the zeta function can fluctuate the sizes. So if you integrate these things, you may get a really large contribution from very rare points, but very large contributions which would completely destroy your test. Yeah. So the idea was to mollify the zeta function. That is to say, to multiply by something else. If you multiply, the zero will still be there, right? I love the property. 0 times something is always 0. Yeah, and I always say, my student, never divide by 0. All right. Okay, anyway, so if you multiply by, then you still get zeros, right? But you may multiply by something that mollifies the zeta function, makes it smaller. How to know it when you don't even know much about the distribution of values of zeta function? Well, you don't need it. Just one inverse of that really dumps a bit the size. So if you take multiply by the inverse of zeta function, well, you get 1, but then you cannot control it. So you really would like to take something that pretends to be inverse of the zeta function. So you take a Dirichlet series representation of the inverse of zeta function. That means maybe this function appears there, and you chop that series, hoping that's a really a very brave idea that if you cut that things, it still mimics the inverse. And you can see later it doesn't do the job perfectly, but it does do the job pretty well. Oh boy. I'm sorry, but I have really little time left for this. We'll start late, yeah. And right, so if you multiply by this mollifier m, and then start doing sign changes, you do better job. But of course, you may be trapped because the sign change may come from the sign change of the mollifier. So Selberg came with a fantastic idea. He knows the best that the square of a number is non-negative, right? And so he constructed mollifier, which is a square of another Dirichlet polynomial, which then this other Dirichlet polynomial mimics the inverse of the square root of zeta function. Okay, fine, no problem here, and that's what he has done. But right, this is. The introduction of mollifier is not really due to Selberg. It was hardly due to it, but also I think earlier one, by what's his name? Yeah. Oh gosh, I forgot him. Old man. Yeah. Right, okay, whatever. Right. But it was not as efficient. One of the things that yeah, Bohr. Right. Yeah. Right. Yeah. One of the things. That Selberg introduced on top of this idea of squaring is smoothing. He was master of smoothing. That Hardy and Leavitt didn't smooth, and if you smooth it when the end point, the cut point is gradually diminishing, that gives you much better performance and much better. It looks like technical. If you apply such smoothing techniques in certain other contexts, you find out it has meaningful arithmetical even meaning. It's hard to say briefly. Anyway, these ideas then were implemented by Selberg into upper bound sieve. Yeah, okay, yeah. Now quickly, Levinson's method. The Levinson method is diametrally different. Opposite, it's to Selberg's, completely opposite to each other. It starts from a linear combination of derivatives of a function. I take just original like him to a function and its derivative. Brian had a fantastic generalizations much further going when you take also linear combinations into account of derivatives of odd order. And it satisfies certain functional equation. There are lots of symmetries needed in order to locate zeros on the line, and not so simple as for the function itself. And then you also have to mollify as before by M of S, let's say. What is interesting that you be integrating this stuff not on the critical line, but to the left to the critical line, a little bit to the left, very little bit. But A, I mean, oops, that's really typo here. There's 1 minus R over log, should be just minus R over log. No 1 in there. Yeah, sorry. Okay, and so it's very little to the left. And the idea is to cancel a variation of the argument and use then a Littwood lemma for rectangles, and you end up with the inequality 4. N double zero, sub double zero means critical zeros which are simple. Because of this choice of linear combination of derivatives, you actually count simple zeros, not even double zeros. That's the observation by, not by Levinson, but Selberg and his Brown later on. So you get a lower bound, as I here in the middle of the page. N of t is the total number of zeros, right, of height up to t, and then minus the integral of this f function, a logarithm of it, that use concavity of logarithm, and end up with the bound that I of t is just the mean value of absolute value of f of t. This is our g function mollified, right? You see, and it's a challenge because of mollification. That integral is bounded by a constant asymptotically. Because mollification does the job like this, and when the constant is very, you can see this cannot be smaller than 1, but if it is not large, then you succeed to get positive density of zeros. Somehow I would like to say that Selberg and Levinson's method, as I said, are completely different. But Selberg doesn't take any risk. It's just you get positive density if you succeed to finish the calculations. You know, I mean, you don't need to use computers to see that it does produce positive density of zeros. I mean, for GL1 guy, for GL2 it's a harder thing anyway. But Levinson's method is a gumbo. I mean, you can end up with negative lower bound for the number of zeros if your estimations for these integrals are crude or if the mollification is not good. However, there's a great advantage of Levinson's method over Selberg is that it opens a possibility to get 100% of zeros, provided your mollification is perfect or nearly perfect. Because if so, f would be on average 1, and it is on 1, log of 1 is 0, and then there's a contribution of these negative terms here from the variation of the arguments, which I didn't say, is really rather small. Well, so that's how one would like to open a question: does it exist, a perfect mollifier? And there's a lot of, I would say, different or disagreement in the literature about whether a perfect mollifier exists or not. If you are expert in sieve theory, you may doubt because there is a parity problem there. You may not able to abide by mollification to really mimic perfectly the inverse of zeta function on the line, critical line. Actually, look, there are zeros there. The inverse is then infinity, etc. But you are off the line a little bit to do that, right? So there was a controversy. Finally, there was there are lots of beautiful works in this golden time of Stillwater. Brian Conrey, David Fermer, and then Goldstone, Sukonek, and Ghosh wrote lots of papers about speculating about length of mollifier and whether this could be perfect or not. Remember that the Selberg method up front, at least on its face, doesn't do that job because you do integration over short intervals, and if you believe that you can catch 100% of zeros in counting, means zeros has to be equidistributed because the same length is for each one. And we know from prediction, of course, per correlation conjecture of Montgomery that they are not equidistributed with respect to the Lebesgue measure. The other density function comes there, right? All right. So here is a There are some improvements because the longer modifier you take, the better result. There are some improvements for families of functions, not just for individual one. And we spent with Peter a lot of time and wrote papers about families, lots of families. And the idea, just briefly speaking, is that you have extra orthogonality. Families are independent, not only just algebraically, but also spectrally. And you can afford, by doing number theory this way, to get longer modifier. And that means larger percentage of zeros. For example, large C for characters, Conrey and myself and Sander Riemann established. So we got something like 57%, or 60% for families. So more than 50. Wow. Yeah, right. Yeah. And that's when modifier is as long as you can predict, say, by natural way, when modifier is of length t, right, or the conductor. But David Farmer has one fantastic speculation in his paper saying that modifier could be infinitely long. I mean, much longer. I mean, and also predicted that that would give 100% of zeros. Yeah. However, there's a little bit of argument of assumption there. I mean, you are really mixing that with I mean, like in Selberg method, instead of short intervals, you have to take lengths of intervals related to the zeros themselves because they are not equidistributed. So this analysis is based on evaluation of mean values over the zeros. So you have to assume Riemann hypothesis and other things to prove less than Riemann hypothesis. Right? But educationally, it's good. If you assume Riemann hypothesis, you can prove there are 100% of zeros on the line. Right, yeah, right, yeah, right, yeah, right, etc. But so the modification may work anyway. So what we do here today is with Brian, and we are looking for, so we shall actually produce perfect modifier. Under one assumption, right? So let's wait for the assumption, right? Yeah, right, okay. So again, let's start in general, even though it will be very specific. Take L function as before, and with coefficients which are very often zero, vanish, or let's say sufficiently small, very often. So we call it lacunary L function. We measure the lacunarity by this inequality, lambda n over n, and n segments bounded by blah, 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 this epsilon over there. One thing you can sniff from this inequality is that it tells you that lambda n appears less often than prime numbers. Prime numbers have this 1 over log, and this epsilon in this estimation that makes this difference. You see, so we are assuming something completely unreal. You see, but not completely unreal. There are L functions that are lacunary, like let's take saturate this, and you have lambda p is less than 1 more often than larger one, and then average is less than. However, never less than the prime numbers will just the lambda p less than 1, but that doesn't mean it's very small, right? So anyway, so it is unreal hypothesis, but as I said, for educational reason, it's good to speculate to see how things work and how good things will this special assumption does for the zeros. Again, we take the inverse. Rho m of is the coefficient of the inverse, and we create a modifier, which is a truncation of the. Oops, m2 minus s is missing here, as you can see, right? Rho m gm times m2 minus s should be there, and the rho is the coefficients of the inverse. G is the cropping factor, and again, like in Selberg, you do it very carefully with smoothing, and funny enough here in the Selberg, if 1 degree smoothing would suffice, we need 32 degrees. I mean, so E is at the end to succeed. And M is very small. So funny enough, I'm saying that this would be a perfect modifier, and I'm taking the length T to 1/2014. You see, which is not very long, right? It's, well, because of diagonal terms in GL to take care of your approach. You know, lacunarity is the secret. Lacunarity takes you know, it just, even short modifier like this would do the job of modifying the L function, right? Okay, so example, where is the source of lacunary L functions? Take the quadratic number field, not necessarily real or imaginary, just any, and take the ideal class group character psi and L function for this. And so lambda n is just the number of ideals of norm n, not weighted by values of the character. Q, this conductor is actually D in this case, and every character, ideal class character, is bounded by the trivial one, and the trivial one is very special. The trivial one gives us this convolution of one against the character. Character is the Dirichlet character this time, the Kronecker symbol, you see, and we have by Vinogradov or whatever convexity bound, you know, we have this estimation on the bottom of the page. You see it, right? Do you see the bottom of the page? I'm sorry, because I don't know what's going on there. Yeah, you do. Okay. Yeah. So this is what is there. So when you assume that L function is very small, then you have lacunarity. So let me rush first to say the results and then continue conversation. First we have unconditional result. Nothing is assumed. Theorem 1. But okay. So number of simple zeros of height t of the Heckel function here, L of S psi, on the critical line of height up to t, is comparable with the number of the total number of zeros of height t, this time counted with multiplicity. So if I put epsilon of d to be L function at 1 times log d, then we have a result. N0, 0t is equal to blah, blah, 1 plus epsilon to 1/2 times n of t plus O of t. And this is in certain segments, when t is not large and not small, when t is d to 1 of epsilon less than t to, let's say, 2 of epsilon. Right. This is unconditional result. However, it's pretty useless unless epsilon is small. Epsilon doesn't even need to go to 0. It's enough that it's a small number. It would give you certain positive density of simple zeros. But that's what we introduce the concept of exceptional discriminants. If it is infinite sequence of those discriminants that epsilon of d goes to 0. So if so, then corollary from the theorem says that 100% of the zeros of L of S psi are simple and on the critical line in certain segments, as it's written down over there, right? Well, very attractive is a special case of it. That's what we really want to do, motivated at first, is when for the trivial ideal class character. Because then L function, then the kin zeta function.
This is short of getting the zeros on a picket fence, which is Doring.
Picket,
right?
yeah.
You're not 100%.
No, you can't, yeah. Yeah, right, yeah.
That would require much stronger.
Yeah, yes, of course, it could be much stronger, but we didn't want to make a mess. Yeah. You could do much more. Actually, let me say, thanks for saying that. If we assume something much weaker about L function, I mean, but stronger, excuse me, right? You know, rather than epsilon, the argument technically would be 100 times simpler. It's so hard to get exactly what we said. There's epsilon times log d. It has a meaningful assumption, by the way, if you look compared with the class number problem. I have no time for that. All this effectiveness and not effectiveness, blah, 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 like that. So that's how we're really we are eager or we are really stubborn to take this weak assumption about L of 1 chi less than epsilon over log d. If you say log d to minus 2000, things will be much simpler, technically, but the same philosophy actually, like that. Anyway, the corollary for the trivial character is probably the most spectacular. It tells you that if there exists an infinite sequence of exceptional discriminants, then the Riemann zeta function itself, nothing to do with L function, has 100% zeros in certain segments of the critical set. So that's what in the title, sometimes. But it's an ambiguous. I mean, it's a double meaning sometimes here. Sometimes means in certain segments, and means that maybe never if you prove that there's no such character, right? Yeah. So right, and so this other thing is that the zeros are simple because we took the linear combination of L and L prime, not the higher powers. That's the extra bonus from Levinson's method. So if that's simple, that we also know that this 100% of zeros of zeta function do not share zeros of L function itself. So they are distinct also, right? So the zeros don't see each other, right? Yeah, okay, yeah. All right, so I really was tempted to show some ideas because that's where the essence of this lacunarity comes. I don't know how much time I really have. I started late, but it's now 9 minutes after 12, so should I start doing that or not? Because, oh, it's up to me? Okay, so, yeah. Now, who's the boss here? Yeah. Maybe 15
minutes.
No, really? Oh, okay. In the schedule, it says 12:10, and it's 12:10 in my Casio.
Yeah. You started at 11.
Yeah, I know, but it's in print. It's different. Yeah. All right, so let's go. Yeah, just. Yeah. All right. Yeah. No, it's all technical, but I tell you, this technicality really shows certain essence of it because that's the whole game here. Is to show certain peculiarities, essential features of things. So you have this G function, linear combination of L function and derivative, scaled down by logarithm naturally, and you want to mollify it. So if you want to mollify it, you would like to represent this as a Dirichlet series or Dirichlet polynomial. You just want to cut it. That's not a big deal. By functional equation, you can chop it at the square root of the conductor. But we have chosen a longer polynomial to approximate G of S of length n, which is dt squared, rather than square root of that, for two reasons. One reason is that there is no root factor present in this. That means you avoid a big problem with cross terms. Whoever knows what this means, right? You know, cross terms are also contributing or how to be taken care properly. And I tell you, this is if you are looking for 100% zeros, you cannot lose a constant in this estimation of this integral. And so if you drop one part of this approximate functional equation, you are dropping a constant. How can you get 100%? Right? So we don't want to mess with the root number here, right? And we don't. So we take a longer polynomial. But then we partition this function 1 minus x into two parts, but not by sharp cut at 1/2, but about beta and alpha close to 1/2 each, but not exactly. And then we apply, function equation of Poisson summation for b of x, go to the dual, right? You may say, wait a minute, now you have a root number again in the dual. It is true. Right? However, b of x is flips from b star of x vanishes at small at the beginning. So the contribution of the terms at the beginning of the series would be minor, like that. So that's what approximate function would not reveal. So you have to do that, right? And so there's a representation here of G in terms of a little bit shorter polynomial, and then with root number times the dual one. And then you start modifying that. Modify what? You have two different polynomials, and you have to modify by one polynomial, right, M. And do the perfect job for both simultaneously. We are not on the critical line. We are to the left a little bit of the critical line, you see. So you may say you never get 100% because modifier would, if it does a good job for one, it doesn't do the good for the other. But now the lacunarity takes place, you know, here. You just simply take inequality, right? First of all, pick up one from the equal to one contribution, and then apply triangular inequality. Ignore the root number, and then just hope that that other one over there with this dual is small because the coefficients are small at the beginning. And if the beginning is the problem, right? So the coefficients are convolutions of our modifier against coefficients of the L function or G function, right? And suppose L is square free, then it is equal to lambda of L times convolution of Möbius function, because the inverse mimics the Möbius function against the smooth test function G and H here. There are two meanings of it. Lambda of L is lacunary by our assumption, so lacunarity is preserved, and but on top of that, you have also kind of a sieve weights because of the modification. And sieve weights tell you that L is essentially supported almost primes. That's very, very important feature, because if L, at the beginning of the series, you cannot observe lacunarity. Lacunarity starts showing later. So the sieve weights take care of killing very small terms at the beginning, like in sieve. Well, I call it sieve weights. It's not called sieve in Levinson's method, but it has the same, you know, function there, right? And so it happens, which is fortunate, that the diagonal terms from the entire main term, the off-diagonal terms do not contribute much. And there is there's a little bit of sequence of inequalities you can read if you want from there, you see. And as I said, small l does not need the lacunarity of lambda L. First of all, it would not even be there necessary like that. However, let's see where I am here. Okay, that's too early. Yeah, yeah. Right. I mean, why I didn't write this on in my transparency? I have it in my notes. Yeah, it was last night when I came from Zurich. Yeah. So the question is, why only diagonal terms contribute? We know that on the critical line, it's really much more sophisticated terms of the diagonals. The point is that if you make off-diagonal terms have a shifted Rankine-Selberg type convolution, be lambda of L times lambda of L plus H different from 0. And lambda is lacunary, and lambda L plus H are lacunary, but they are independent. So you are really, because H is not 0, so you have much more lacunarity of the diagonal terms than on the diagonal. That's why they contribute insignificant amount. Yeah. Well, lambda 0 and is non-negative, yeah. Yeah, right, yeah, okay, but for, just in on estimations, like that. Okay, and there are lots of, over years, yes, we are working on this stuff with different people, you know, Peter in particular, but we have tried to prove that such exceptional characters do not exist. lots of beautiful results. Peter has his own with Zaharescu. I don't have no time to mention right now that, and then also the spacing of zeros of zeta function of Riemann. The impact of existence of this character is absolutely unlimited, so to speak, like that. So either either way, whether you have this exceptional zero or not, or exceptional character, I would prefer. Remember, never mention zeros because it's all about a function of characters. Like that. So whether it exists or not, either way you like the situation, because if it doesn't exist, then you have beautiful results about class numbers and other things like that. If it exists, then you have even better results about prime numbers, going even beyond the threshold of the Riemann hypothesis, even that far. So you really sometimes like this guy do exist, and some people even believe that it does exist, not me though, and so I don't give names. but anyway, sometimes we wish the exceptional character long life. Sometimes we wish it doesn't exist. And meanwhile, happy birthday, Peter.
Are there any questions or comments?
Yes?
Fence over a long range?
Yeah.
Is it in your theorems? Are you producing zeros in a picket fence over a very long range? Is that
yes,
what's
you
happening?
can do much longer, but for the transparency, for the talk, I chosen the easiest way of showing things. Much longer than what we said. But right.
I think the question is, I think if you assume that L1 chi is much smaller,
Yes.
then you get that effect. So he's not assuming L1 chi is that small, right?
Yeah, that was our challenge. We didn't want to assume, yes?
But it's small enough to mess up the GUE.
Oh yeah, fantastic subject, right. You see, yes, it is, actually. This issue was actually addressed in a talk by his Brown in Seattle when he said that showed, never published actually, he showed that if the exceptional character or zero exists, but much stronger assumption than we do here, then the percolation theorem is false. I mean, zero tends to be actually equidistributed. So somehow it's consistent that we succeeded by Levinson's method to get 100% conditionally, right, like that, and my objections or reservation to Selberg method. Maybe because of the existence of the assumption of the sectional character, the Selberg method will also work because the zeros will be equidistributed with respect to the Lebesgue measure.
Have you tried?
No, we didn't. Yeah, because it depends on the weather. Oh yeah. I mean, one day we will not prove there exists such a character, another day we won't prove it doesn't. So, I mean, it's really trapped in this situation, but I like it. Yeah. So, Jeff, did I answer your question?
My question was, if you have to actually imply under that hypothesis that the GUE is not satisfying?
Well, let's answer this way. I didn't try it, but I believe it would violate it. Yes.
I think the answer would be that if you localize GUE, then the method would violate it.
Yeah.
It would produce kind of result. As it stands, GUE would say, the simplest statement of GUE is that if you look at all zeros up to t, if you're only producing lacunar, very minute intervals.
Yeah, right. Yeah, that's only in certain segments.
Formally, you don't.
Yeah. So it's amazing, actually, that it's actually nice that we just it still does not convince some believers that such exceptional character exists. It is really in violation of many standard or beautiful things that we predict in number theory, but it doesn't really give a rigorous contradiction. So it is fascinating.
Okay, I think we should break for lunch. We're a little bit behind schedule, and I don't want everyone to be rushed. So let's move this, the starting time by 10 minutes to 1:50, and we'll make it up somehow. So we'll start at 1:50 sharp.